dimensionless. We take a standard equation of state P as gamma minus 1 mu, which will give you dust. If gamma is 1, it'll give you radiation. If gamma is 4/3, and so on, and the Hubble parameter. And then from this, from the equations we've had, you can easily deduce that S dot is H times S, and omega dot is H omega into 1 minus omega into 2 minus 3 gamma, and these gives you a phase plane for omega as a function of the scale factor. Now this is really quite nice because we want to know how this evolves through the history of the universe, and for ordinary matter, that is for gamma greater than 2/3, you get a fixed point for omega is 1, the critical density. Now that's obvious from here. When omega is 1, omega dot is 0, and so that is an integral curve. The line omega is 1. The line omega is 0 is also an integral curve. That's also obvious. When omega is 0, you get omega dot is 0, and when omega is 1, you get omega dot is 0. Now, if you just look at the signs of this and work it out, what you will find is if you are slightly above here, omega rises and it diverges. And so this is unstable, and this is what underlies what is called the fine-tuning problem that inflation tries to solve. If omega is a little bit above 1, it increases without end. If it is a little below 1, it decreases towards 0, and so this is an unstable line. It is an exact solution. If you are omega 1 at any time, you're exactly omega is 1. You remain with omega is 1 for all time, and that is absolutely independent of the equation of state. That is for all equations of state. But for ordinary matter, you diverge. Now, there's a problem with this diagram, and the problem is you can't see what happens to these curves as they go up. And in fact, omega diverges. I mentioned this briefly yesterday. Omega diverges when the universe reaches its maximum radius, because at that time the energy density is finite. But as you reach the top and you start recollapsing, the Hubble constant is 0, and at that instant, omega is infinite. Now, there's nothing wrong with the physics. You just have chosen a variable which is not a terribly good variable. Well, there's a nice way to deal with that. What we can do is we can take an arctan of the variable, and then omega is infinity becomes a standard line across here, as you can see there. And what you can do is you can just continue right through, and you get here the complete phase space. What you had above was a half phase space. And what you get here is for the models to recollapse, omega goes to infinity, which is when the model has reached its maximum. The radius scale function has reached a maximum. S dot is 0 at this instant. The Hubble constant is 0. Omega is infinity. And then it recollapses to this future singularity. So that's the past singularity, and that is the future singularity. And what this now gives you is a time in a reverse invariant phase plane. In fact, for every expanding model, there is a contracting model in this diagram, and that's the complete phase space for standard matter for omega as a function of S. Now, if you have matter with gamma less than 2/3, the sign here changes and you get the opposite effect taking place. What you get is that omega is 1 becomes an attractor. So it was a repeller up here, but it becomes an attractor here. And as the universe evolves, omega tends towards 1. And this is the famous solution that inflation gives you for the reason that the universe is very close to flat nowadays. It's because for an inflationary equation of state, which will be gamma less than 2/3, the omega is 1 acts as an attractor. Now, in fact, in inflation, what happens is initially, you probably don't have inflation, you probably have radiation, you might have a quantum era. What I've drawn here is the complete diagram of omega for an inflationary universe. Now, there's some initial period where you don't know what's happening because that's the quantum gravity domain. You then have an ordinary matter, a radiation era, when omega diverges from 1. Then a scalar field takes over, and this will be discussed for you by Professor Roy Martins later on, and then omega is pulled towards 1. At the end of inflation, the scalar field comes to an end, it gets converted to radiation, and you go back to an ordinary universe, ordinary matter, and then we reach today, that vertical line here, and the universe carries on to infinity. And so this is the phase plane. The omega diverges until inflation starts. It then gets pulled towards 1 as inflation takes over. At the end of inflation, it starts diverging again from 1, excepting if you are at the critical density, in which all of this is irrelevant. You stay at 1 for all time because you are at exactly that critical density. And this shows that completed again in the same way as before, with omega is infinity there. And it's quite, now, we must take this with a little pinch of salt. I've done this as if the physics is time reversible. Now, the turning out of inflation and the turning off inflation is actually a process which is not time reversible. So you must take the upper half of this, which a little pinch of salt. That would only be the case if inflation turned off and turned on again in exactly the time reverse of the way it happened in the expanding phase. But you see a very interesting result coming in here. When you put the whole diagram in, you can see a fixed point here. It's an unstable fixed point because it is a saddle point. That occurs for omega is infinity. What is that? That is the time when the Hubble constant is 0. What could this solution be? If you think about it, it is the Einstein static universe. And what you see is in this model, there are two starting points. There is the diverging point, the Einstein de Sitter universe at the beginning, I've mentioned already. There is the Milne universe in the far future as the future attractor. And there is now the Einstein static universe, and there are solutions which start at the Einstein static, which asymptotically tend to the Einstein static, and that is the new feature we have here. And this is a completely non-singular state of the universe. This is the highly singular Einstein de Sitter state, but this is the Einstein static non-singular state. And so what you get to see here is the possibility of the universe models which I have recently been developing with Roy Martins and Jeff Murrigan and others, in which you start off asymptotic to the Einstein static, which is completely non-singular. You go into an inflationary expansion phase. The inflation comes to an end. And then what happens in the far future depends on what happens at that time, but in this case it would recollapse and come back towards an initial singularity again, or an Einstein de Sitter, depending on this time reverse, which, as I've said, in fact we don't expect the solution to be the turning on and off of inflation to be time symmetric. But the thing that you're seeing here is, firstly, the standard inflationary models, if they are less than 1, what you do is you get where omega increases, it decreases towards 0, and then it comes back towards 1, and then it goes down to 0 in the far future universe. If omega is greater than 1 for ordinary models, omega increases, decreases towards 1. It increases, it goes through infinity, and you enter your collapse phase. And what happens here depends on the time reverse dynamics. And you get this new possibility of a model which is asymptotic to the Einstein static in the past. It is completely non-singular. It expands into an inflationary era, then the post-inflationary era, and then what happens in the collapse phase depends again on the time reverse dynamics. And one point which I think I must make out of all of this, which is a lot has been made, and you will know about this, about how close omega is supposed to be to 1 today. What you can see is that is an unstable situation. Even if omega is very close to 1 today, unless you are at exactly the critical domain, this will not remain true. Either omega will go on to diverge or it will go on to 0. But in fact, in inflationary models, there is, even if however close omega is to 1 today, that is an unstable situation. You also do the following. Taking the models which start off at the Einstein static, choose a time today, like that time there. There exist inflationary models which will give you any value you like for omega today. There are models, as you can see from that phase plan diagram, that will give you any value you like. A lot of the inflationary literature is very confusing about this. It says inflation must lead to values very, very close to 1. Well, in fact, that is actually not really the case. Yeah. The Einstein static model is completely unstable.
Yeah, but I see these diagrams as like a stability analysis.
Yeah.
And he's saying kind of like, when he says you're developing one which starts at Einstein static and the inflationary thing, you have different solutions as you are moving along the fluid flow.
be looking at this later on, I think. But I'm not sure. The solutions will join, well, there'll just be one solution, and there's no question it exists. The analytic approximations we will use for it at different times will vary, and that's where complication will come in. Okay, now, oh dear. Okay, now, I want to just make one other comment about the inflationary models, which is as follows. What you've got is you've got an energy density is a half phi dot squared plus V of phi, and effective energy density, and the pressure is a half phi dot squared minus V of phi. And you put them into the field equations which we had written down and which are in the notes that you've given. And the question is, how general is the behavior that is allowed? To put it another way, if I choose